Now, with your program in place that can read in data from some file, do some analyses, and either display the results on the screen or write the results to a file, you're probably ready to visualize the results in some form of plot, and that's what we'll deal with today. How can you process your data and create publication quality plots? The focus here is on publication quality because in the sciences, that's ultimately what we want to do. And we want to create a plot in a way that allows us to take it as it comes from the processing pipeline, add it into our manuscript, and be done with it. There are several reasons for doing that. One is reproducibility. Again, you want to be able to take your data and have all the steps written down that happen to your data until you make the figure that you include into your manuscript. The other piece is that data change. You may have daily updates where a sensor in the field, snow depth measurement, water gauge, or soil moisture is being recorded on a data logger in the field, and then data are transmitted to your lab once a day or several times a day. Or you have a region in the field that you go to every year and you collect new data. Then you come back and you want to create a time series that incorporates the existing data and the new data without having to manually intervene too much. It might be that the analysis technique has changed, some different way to remove outliers or noise, different kind of filtering or smoothing. It might simply be that you forgot something, you found data that you didn't think existed and that could be included, or files just ended up in a different place and you need to remake your plot. So everything that you do to a figure manually will have to be repeated after each data update. And that's a huge source of error. And it's incredibly tedious to do these things that could be automated. My recommendation is to automate figure creation as much as possible. Have the figure created, spend a lot of time up front ensuring that the story that your data is telling can be told without Photoshop or Illustrator interference. How do you do that? You set up your workflow that one action initiates data ingestion, leads to analysis and modeling. Perhaps after these steps, a file is created that saves the results of more complex computations. But then eventually, the figure is being automatically created, and that can happen in the same script. And then you can invoke that figure creation script separately too. What you have to keep in mind is that figures are major scientific products. Setting up a good figure can easily take a day or more. It can take weeks. And that's okay, because good figures will get reused by others, hopefully crediting your work, but it will be an advertisement of your findings. Importantly, though, you need to know your audience. The audience of a lecture is not necessarily the same as a department seminar or a journal article or a brief meeting presentation or outreach to the general public. What we most often do when we make a figure, we make it for a journal article. These figures are incredibly dense in their information content. They're oftentimes quite busy because your audience there is a reader who has time to read through the caption, the surrounding text, and understand all of the elements that you packed into this very tight space, which is often required because some journals limit the number of figures that you can use. Figures can't be larger than a certain size, and other constraints. In a seminar or kind of a speaking environment, however, you do not want to use the densest version of a figure that comes from a paper. If you bring up a figure that has 5 different time series in 5 colors, 3 more insets that show other things, you will not have control over which pieces of that figure your audience is looking at. You can try to guide them through this, but most likely people are very interested in the visually most appealing part of your plot and aren't necessarily even going to follow what you're saying. So for a seminar, you'll bring up your figure in layers. You use a base layer with some information, and then you add information on as you talk about it. And with that, you guide the attention of your listeners. And one way to create figures that are easily adaptable is to use vector graphics instead of raster graphics. We have vector graphics here on the left-hand side and an example of raster graphics on the right-hand side. There are two major differences between vector and raster graphics that are obvious to any user. For raster graphics, if you zoom in too far, you see pixeled edges. And if you zoom into vector graphics, the edges remain smooth of your objects. The way a raster image works is that it is a matrix or a table of columns and rows. And the information that a raster image stores is that in column 5, row 10, we have that percentage of red, that percentage of green, and that percentage of blue to make up our color that we're displaying. So in this red circle, we have 100% red, 0% green, 0% blue. In this piece, in this column 10, row 10, whatever it is, we have 50% blue, 50% red, 0% green, making purple. In vector graphics, what you store is, here's the center of a circle. That circle has this radius. Draw the circle for me. And the circle gets drawn in the display. And that means that the closer you zoom in, that circle can get rendered with perfectly unpixelated edges. What this brings with it is that the program that you use to edit these types of files knows that this circle is an object that has a center, a radius, and some fill color. And it can allow you to select that object of the circle that is red individually from the circle that is blue. So you can drag that circle around and that circle separately, and you will have two perfectly round circles. One is blue, the other one is red, and there isn't any overlay anymore. You cannot do that in a raster image. You can try to select this circle here and then drag it out, but then this piece of the red circle, the intersection here, is going to be also dragged away, and you need to somehow repair what you ate away and change the color inside the circle here, which gets really complicated if you have compressed image formats like JPEG too, because it gets kind of fuzzy around the edges. So keep that in mind. Vector images, you can manipulate individual objects. You can take layers off or layers in. Raster images, you cannot. The formats are JPEG, GIF, PNG, or rastered PDF. For raster images, for vector images, we have Adobe Illustrator, EPS, scalable vector graphics, and PSD, as well as PDF. While before I said that you should automate as much as possible your figure creation, if you make vector graphics, you still have the opportunity to customize an automatically generated figure to your audience. Vector graphics allow you to simplify the figures very easily without degrading their visual presentation. There are a number of books out that try to help you making good scientific figures. One of the leaders in the field is, without doubt, Edward Tufte. He has a series of books out on visual representation of data. One of the earlier ones is The Visual Display of Quantitative Information, which really should be a must-read for any science student. But there's a long line of publications that all try to convey information that remains current to this day.